Newton's laws of motion are three physical laws that together laid the foundation for classical mechanics. They describe the relationship between a body and the forces acting upon it, and its motion in response to said forces. They have been expressed in several different ways over nearly 3 centuries, and can be summarized as follows. First law: when viewed in an inertial reference frame, an object either remains at rest or continues to move at a constant velocity, unless acted upon by an external force. Second law: phi equals mr. The vector sum of the forces F on an object is equal to the mass m of that object multiplied by the acceleration vector a of the object. Third law: when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. The 3 laws of motion were first compiled by Isaac Newton in his Philosophiae Naturalis Principia Mathematica, first published in 1687. Newton used them to explain and investigate the motion of many physical objects and systems. For example, in the 3rd volume of the text, Newton showed that these laws of motion, combined with his law of universal gravitation, explained Kepler's laws of planetary motion. Overview: Newton's laws are applied to objects which are idealized as single-point masses, in the sense that the size and shape of the object's body are neglected to focus on its motion more easily. This can be done when the object is small compared to the distances involved in its analysis, or the deformation and rotation of the body are of no importance. In this way, even a planet can be idealized as a particle for analysis of its orbital motion around a star. In their original form, Newton's laws of motion are not adequate to characterize the motion of rigid bodies and deformable bodies. Leonhard Euler in 1750 introduced a generalization of Newton's laws of motion for rigid bodies called the Euler's laws of motion, later applied as well for deformable bodies assumed as a continuum. If a body is represented as an assemblage of discrete particles, each governed by Newton's laws of motion, then Euler's laws can be derived from Newton's laws. Euler's laws can, however, be taken as axioms describing the laws of motion for extended bodies, independently of any particle structure. Newton's laws hold only with respect to a certain set of frames of reference called Newtonian or inertial reference frames. Some authors interpret the first law as defining what an inertial reference frame is. From this point of view, the second law only holds when the observation is made from an inertial reference frame, and therefore the first law cannot be proved as a special case of the second. Other authors do treat the first law as a corollary of the second. The explicit concept of an inertial frame of reference was not developed until long after Newton's death. In the given interpretation, mass, acceleration, momentum, and force are assumed to be externally defined quantities. This is the most common, but not the only interpretation of the way one can consider the laws to be a definition of these quantities. Newtonian mechanics has been superseded by special relativity, but it is still useful as an approximation when the speeds involved are much slower than the speed of light. Newton's first law. The first law states that if the net force is zero, then the velocity of the object is constant. Velocity is a vector quantity which expresses both the object's speed and the direction of its motion. Therefore, the statement that the object's velocity is constant is a statement that both its speed and the direction of its motion are constant. The first law can be stated mathematically as: consequently, an object that is at rest will stay at rest unless an external force acts upon it. An object that is in motion will not change its velocity unless an external force acts upon it. This is known as uniform motion. An object continues to do whatever it happens to be doing unless a force is exerted upon it. If it is at rest, it continues in a state of rest. If an object is moving, it continues to move without turning or changing its speed. This is evident in space probes that continually move in outer space. Changes in motion must be imposed against the tendency of an object to retain its state of motion. In the absence of net forces, a moving object tends to move along a straight line path indefinitely. Newton placed the first law of motion to establish frames of reference for which the other laws are applicable. The first law of motion postulates the existence of at least one frame of reference called a Newtonian or inertial reference frame, relative to which the motion of a particle not subject to forces is a straight line at a constant speed. Newton's first law is often referred to as the law of inertia. Thus, a condition necessary for the uniform motion of a particle relative to an inertial reference frame is that the total net force acting on it is zero. In this sense, the first law can be restated as: in every material universe, the motion of a particle in a preferential reference frame I is determined by the action of forces whose total vanished for all times when and only when the velocity of the particle is constant in I. That is, a particle initially at rest or in uniform motion in the preferential frame I continues in that state unless compelled by forces to change it. Newton's laws are valid only in an inertial reference frame. Any reference frame that is in uniform motion with respect to an inertial frame is also an inertial frame, that is Galilean invariance or the principle of Newtonian relativity. Newton's second law. The second law states that the net force on an object is equal to the rate of change of its linear momentum p in an inertial reference frame. The second law can also be stated in terms of an object's acceleration. Since Newton's second law is only valid for constant mass systems, mass can be taken outside the differentiation operator by the constant factor rule in differentiation. Thus, where F is the net force applied, m is the mass of the body, and a is the body's acceleration. Thus, the net force applied to a body produces a proportional acceleration. In other words, if a body is accelerating, then there is a force on it. Consistent with the first law, the time derivative of the momentum is non-zero when the momentum changes direction, even if there is no change in its magnitude. Such is the case with uniform circular motion. The relationship also implies the conservation of momentum. When the net force on the body is zero, the momentum of the body is constant. Any net force is equal to the rate of change of the momentum. Any mass that is gained or lost by the system will cause a change in momentum that is not the result of an external force. A different equation is necessary for variable mass systems. Newton's second law requires modification if the effects of special relativity are to be taken into account, because at high speeds the approximation that momentum is the product of rest mass and velocity is not accurate. Impulse. An impulse J occurs when a force F acts over an interval of time it, and it is given by. Since force is the time derivative of momentum, it follows that this relation between impulse and momentum is closer to Newton's wording of the second law. Impulse is a concept frequently used in the analysis of collisions and impacts. Variable mass systems. Variable mass systems, like a rocket burning fuel and ejecting spent gases, are not closed and cannot be directly treated by making mass a function of time in the second law. That is, the following formula is wrong. The falsehood of this formula can be seen by noting that it does not respect Galilean invariance. A variable mass object with φ equals 0 in one frame will be seen to have φ = 0 in another frame. The correct equation of motion for a body whose mass m varies with time by either ejecting or accreting mass is obtained by applying the second law to the entire, constant mass system consisting of the body and its ejected accreted mass. The result is where u is the velocity of the escaping or incoming mass relative to the body. From this equation one can derive the equation of motion for a varying mass system, for example, the Tchaikovsky rocket equation. Under some conventions, the quantity where dm dt on the left-hand side, which represents the advection of momentum, is defined as a force and is included in the quantity f. Then, by substituting the definition of acceleration, the equation becomes φ equals ma. Newton's third law. The third law states that all forces exist in pairs. If one object A exerts a force Fa on a second object B, then B simultaneously exerts a force Fb on A, and the two forces are equal and opposite, Fa equals Fb. The third law means that all forces are interactions between different bodies, and thus that there is no such thing as a unidirectional force or a force that acts on only one body. This law is sometimes referred to as the action-reaction law, with Fa called the action, and Fb the reaction. The action and the reaction are simultaneous, and it does not matter which is called the action and which is called reaction. Both forces are part of a single interaction, and neither force exists without the other. The two forces in Newton's third law are of the same type. From a conceptual standpoint, Newton's third law is seen when a person walks, they push against the floor, and the floor pushes against the person. Similarly, the tires of a car push against the road while the road pushes back on the tires. The tires and road simultaneously push against each other. In swimming, a person interacts with the water, pushing the water backward, while the water simultaneously pushes the person forward. Both the person and the water push against each other. The reaction forces account for the motion in these examples. These forces depend on friction. A person or car on ice, for example, may be unable to exert the action force to produce the needed reaction force. History, Newton's first law, from the original Latin of Newton's Principia, translated to English, this reads, the ancient Greek philosopher Aristotle had the view that all objects have a natural place in the universe, that heavy objects wanted to be at rest on the earth and that light objects like smoke wanted to be at rest in the sky and the stars wanted to remain in the heavens. He thought that a body was in its natural state when it was at rest, and for the body to move in a straight line at a constant speed an external agent was needed to continually propel it, otherwise it would stop moving. Galileo Galilei, however, realized that a force is necessary to change the velocity of a body, that is, acceleration, but no force is needed to maintain its velocity. In other words, Galileo stated that, in the absence of a force, a moving object will continue moving. The tendency of objects to resist changes in motion was what Galileo called inertia. This insight was refined by Newton, who made it into his first law, also known as the law of inertia. No force means no acceleration, and hence the body will maintain its velocity. As Newton's first law is a restatement of the law of inertia which Galileo had already described, Newton appropriately gave credit to Galileo. The law of inertia apparently occurred to several different natural philosophers and scientists independently, including Thomas Hobbes in his Leviathan. The 17th-century philosopher and mathematician René Copyright Descartes also formulated the law, although he did not perform any experiments to confirm it. Newton's second law, Newton's original Latin reads, this was translated quite closely in Mott's 1729 translation as, according to modern ideas of how Newton was using his terminology, this is understood, in modern terms, as an equivalent of the change of momentum of a body is proportional to the impulse impressed on the body, and happens along the straight line on which that impulse is impressed. Mott's 1729 translation of Newton's Latin continued with Newton's commentary on the second law of motion, reading, if a force generates a motion, a double force will generate double the motion, a triple force triple the motion, whether that force be impressed altogether and at once, or gradually and successively. And this motion, if the body moved before, is added to or subtracted from the former motion, according as they directly conspire with or are directly contrary to each other. Or obliquely joined, when they are oblique, so as to produce a new motion compounded from the determination of both. The sense or senses in which Newton used his terminology, and how he understood the second law and intended it to be understood, have been extensively discussed by historians of science, along with the relations between Newton's formulation and modern formulations. Newton's third law, translated to English, this reads, Newton's scholium to this law. Whatever draws or presses another is as much drawn or pressed by that other. If you press a stone with your finger, the finger is also pressed by the stone. If a horse draws a stone tied to a rope, the horse will be equally drawn back towards the stone, for the distended rope, by the same endeavor to relax or unbend itself, will draw the horse as much towards the stone, as it does the stone towards the horse, and will obstruct the progress of the one as much as it advances that of the other. If a body impinges upon another, and by its force changes the motion of the other, that body also will undergo an equal change, in its own motion, toward the contrary part. The changes made by these actions are equal, not in the velocities but in the motions of the bodies. That is to say, if the bodies are not hindered by any other impediments. 4. As the motions are equally changed, the changes of the velocities made toward contrary parts are reciprocally proportional to the bodies. This law takes place also in attractions, as will be proved in the next scholium. In the above, as usual, motion is Newton's name for momentum, hence his careful distinction between motion and velocity. Newton used the third law to derive the law of conservation of momentum. From a deeper perspective, however, conservation of momentum is the more fundamental idea, and holds in cases where Newton's third law appears to fail, for instance when force fields as well as particles carry momentum, and in quantum mechanics. Importance and range of validity. Newton's laws were verified by experiment and observation for over 200 years, and they are excellent approximations at the scales and speeds of everyday life. Newton's laws of motion, together with his law of universal gravitation and the mathematical techniques of calculus, provided for the first time a unified quantitative explanation for a wide range of physical phenomena. These three laws hold to a good approximation for macroscopic objects under everyday conditions. However, Newton's laws are inappropriate for use in certain circumstances, most notably at very small scales, very high speeds or very strong gravitational fields. Therefore, the laws cannot be used to explain phenomena such as conduction of electricity in a semiconductor, optical properties of substances, errors in non-relativistically corrected GPS systems and superconductivity. Explanation of these phenomena requires more sophisticated physical theories, including general relativity and quantum field theory. In quantum mechanics, concepts such as force, momentum, and position are defined by linear operators that operate on the quantum state. At speeds that are much lower than the speed of light, Newton's laws are just as exact for these operators as they are for classical objects. At speeds comparable to the speed of light, the second law holds in the original form phi equals a dp dt, where f and p are four vectors. Relationship to the conservation laws. In modern physics, the laws of conservation of momentum, energy, and angular momentum are of more general validity than Newton's laws, since they apply to both light and matter, and to both classical and non-classical physics. This can be stated simply: momentum, energy and angular momentum cannot be created or destroyed. Because force is the time derivative of momentum, the concept of force is redundant and subordinate to the conservation of momentum, and is not used in fundamental theories. The Standard Model explains in detail how the three fundamental forces known as gauge forces originate out of exchange by virtual particles. Other forces such as gravity and fermionic degeneracy pressure also arise from the momentum conservation. Indeed, the conservation of form momentum in inertial motion via curved space-time results in what we call gravitational force and general relativity theory. Application of space derivative to overlapping wave functions of pair of fermions results in shifts of maxima of compound wave function away from each other, which is observable as repulsion of fermions. Newton stated the third law within a worldview that assumed instantaneous action at a distance between material particles. However, he was prepared for philosophical criticism of this action at a distance, and it was in this context that he stated the famous phrase "I feign no hypotheses." In modern physics, action at a distance has been completely eliminated, except for subtle effects involving quantum entanglement. However, in modern engineering and all practical applications involving the motion of vehicles and satellites, the concept of action at a distance is used extensively. The discovery of the second law of thermodynamics by Carnot in the 19th century showed that every physical quantity is not conserved over time, thus disproving the validity of inducing the opposite metaphysical view from Newton's laws. Hence, a steady-state worldview based solely on Newton's laws and the conservation laws does not take entropy into account. See also, Euler's laws, Hamiltonian mechanics, Lagrangian mechanics, list of scientific laws named after people, Mercury, orbit of, modified Newtonian dynamics, Newton's law of universal gravitation, principle of least action, reaction, references and notes. Further reading and works referred to, Crowell, Benjamin Light and Matter, especially at section 4.2, Newton's first law, section 4.3, Newton's second law, and section 5.1, Newton's third law. Feynman, R.P. Layton, R.B. Sands, M. The Feynman Lectures on Physics. Volume 1. Pearson Addison Wesley. ISBN A0-8053-9049-9. Fowles, G.R. Cassidy, G.L. Analytical Mechanics. Saunders College Publishing. ISBN A0-03-022317-2. Likens, Peter W. Elements of Engineering Mechanics. McGraw-Hill Book Company. ISBN A0-07-037852-5. Marion, Jerry. Thornton, Stephen. Classical Dynamics of Particles and Systems. Harcourt College Publishers. ISBN A0-03-097302-3. Newton, Isaac, Mathematical Principles of Natural Philosophy, 1729 English translation based on 3rd Latin edition, Volume 1, containing Book 1, especially at the section Axioms or Laws of Motion starting page 19. Newton, Isaac, Mathematical Principles of Natural Philosophy, 1729 English translation based on 3rd Latin edition, Volume 2, containing Books 2 and 3. Thompson, W., and Tayert, P.G. Treatise on Natural Philosophy, Volume 1, especially at section 242, Newton's Laws of Motion. N. M. J. Woodhouse. Special Relativity. London, Berlin, Springer. PA 6. ISBN A1-85233-426-6. External links, MIT Physics video lecture on Newton's 3 laws, Light and Matter. An online textbook, Simulation on Newton's First Law of Motion, Newton's Second Law by Enrique Zimi, Wolfram Demonstrations Project. Newton's Third Law demonstrated in a vacuum.